This video is brought to you by mywayteaching.com.
In this part, we are going to study about potential due to an electric dipole. You already know what is an electric dipole. Okay, 2-point charges separated by a distance. They are called as, it forms an electric dipole, isn't it? An electric dipole, it consists of two charges q and minus q, which is separated by a distance 2a, and its total charge is 0. And it is characterized by a dipole moment vector P. We already know that also. And that dipole vector P is given by the product of charge Q and the distance 2a. And it points in the direction from minus Q to plus Q. Okay. And electric field of a dipole at a point with position vector R, it depends not just on the magnitude R, but also on the angle between R and P. This also we studied. Okay. And now further, the field falls off at large distance, not as 1 by R square, but as 1 by R cube. As distance increase, the field falls in proportion to 1 by R cube, not by 1 by R square. So now let us determine the electric potential due to a dipole and contrast it with the potential due to a single charge. Okay. So for that, you consider a charge. You take the origin at the center of the dipole. Here, this is a dipole plus q minus q, which is separated by 2a, and we are considering the dipole at the we are considering the origin at the midpoint of dipole. Okay, now we know that the electric field obeys the superposition principle, and potential is related to the work done by the field. Electrostatic potential also follows the superposition principle. So potential due to the dipole is the sum of potentials due to the charges plus q and minus q. So that is given by q is equal to potential due to the dipole is nothing but the sum of the potentials due to charge plus q and charge minus q. And that is given by, we know the potential due to charge plus q is q by 4 pi epsilon naught R1, and similarly potential due to minus q is given by 4 pi epsilon naught R2. Okay, and if you take 1 by 4 pi epsilon naught outside, we get 1 by R1 minus 1 by R2, isn't it? Where R1 and R2, as you can see here, it is the the distance of the point P from Q and minus Q. Now, by considering the geometry, we can write R1 square as R square plus A square minus 2AR cos theta. Okay. R square plus A square minus 2AR cos theta, and R2 square, we can write it as R square plus A square plus 2AR cos theta. So we take R much greater than A. And retain terms only up to first order in A by R. And R1 square is equal to, if you take R square common, we get 1 minus 2a cos theta by R plus a square by R square, isn't it? Yes. That is equal to R square 1 minus 2a cos theta by R. So we have taken R very much greater than a. And similarly we can write R2 square as R square 1 plus 2a cos theta by R. Okay. And using the binomial theorem and retaining terms up to the first order in A by R, if you use binomial theorem, we get 1 by R1 is equal to 1 by R 1 minus 2a cos theta by R raised to 1 by 2. Okay. That is equal to 1 plus a by R cos theta. And similarly, by using the binomial theorem, for the second case, we get 1 by R2 is equal to 1 by R into 1 plus 2a cos theta by R raised to minus 1 by 2. And using the equations of these two above and the one we studied before, B is equal to Q by 4 pi epsilon naught R, we get Q by 4 pi epsilon naught 2a cos theta by R square. That is 2a into Q is equal to dipole moment. So P cos theta by 4 pi epsilon naught R square. So P cos theta, we can write it as P dot R cap, where R cap is the unit vector along the position vector OP, and the electric potential of a dipole is then given by V is equal to 1 by 4 pi epsilon naught P dash R cap by R square, where R is very much greater than A. Okay, this is electric potential. So this equation is true only for distances large compared to the size of the dipole, so that higher order terms in that binomial theorem what we have used, they are negligible. So for a point dipole P at origin, however, potential on the dipole axis, if you consider directly at origin, in that case it is given by V is equal to plus or minus 4 pi epsilon naught P by R square. Okay. See, the important contrasting features of electric potential of a dipole due to a single charge The first point is the potential due to a dipole, it depends not just on r but also on the angle between the position vector r and the dipole vector p. We know already, isn't it? And the second point is the electric dipole potential falls off at large distance as 1 by r square, not as 1 by r, as you can see here in this equation. That is the characteristic of the potential due to a single charge. Okay. These two are the important contrasting features of electric dipole potential of a dipole from that due to a single charge. Now let us study potential due to a system of charges. Now we got due to a single charge. What about system of charges? You just consider system of charges Q1, Q2 up to Q1 with position vectors R1, R2 up to Rn relative to some origin. Okay. The potential V1 at P due to charge Q1 is given by the potential V1 at P due to charge Q1. So this is charge Q1 at potential at this point P is given by V1 is equal to Q1 by 4 pi epsilon naught R1 P, isn't it? Where R1 P is the distance between Q1 and P. Similarly, potential at point P due to charge Q2 is given by Q2 4 pi epsilon naught R2P, isn't it? And similarly, if you consider potential at point P due to charge Q3 is given by Q3 by 4 pi epsilon naught R3P, where R3P is the distance between charge Q and the point. So here, and for potential due to other charges, and the equation continues like this only. And by the superposition principle, we know that the potential V at the point P due to the total charge configuration, due to all the charges in the system, is equal to the algebraic sum of the potentials due to individual charges, isn't it? So that we can write the total potential V at point P due to the system of charges is given by the algebraic summation of potential due to individual charges up to Vn, isn't it? And that is given by, if you take 1 by 4 pi epsilon naught common, we can take in bracket Q1 by R1P plus Q2 by R2P, isn't it? And it continues up to Q1 by RNP. So, if we have a continuous charge distribution characterized by a charge density rho of R, we divide it as before into small volume elements, each of size delta V and carrying a charge rho into delta V. And then we determine the potential due to each volume element, and then we sum it up over all contributions and thus determine the potential due to entire distribution. Okay. For a uniformly charged spherical shell, the electric field outside the shell is as if the entire charge is concentrated at the center, and the potential outside the shell is given by Q by 4 pi epsilon naught R. Okay, where Q is the total charge on the shell and R is its radius, and the electric field inside the shell is 0, and this implies that potential is constant inside the shell, which means no work is done in moving a charge inside the shell. Therefore, equals its value at the surface. That is, at the surface, it is the potential is given by 1 by 4 pi epsilon naught R into Q. Okay.